For decades, analog computing carried a reputation for being fast but unreliable. Digital computers won because they could repeat the same calculation with predictable precision. Every value became a sequence of zeros and ones. Analog machines worked differently. They represented numbers with continuously changing physical quantities such as voltage, current, pressure, or resistance. That allowed them to solve some equations almost instantly, but tiny errors accumulated. Components drifted. Precision collapsed as problems became larger. Researchers at Peking University now say they have solved much of that problem. Their team built a foundry-made analog matrix solver using resistive random access memory, or RRAM. The system experimentally solved 16 by 16 real-valued matrix inversion problems at 24-bit fixed-point precision, which the researchers describe as comparable to FP32 digital computing. In Massive-MIMO signal detection, it reached digital-level accuracy after only 3 refinement cycles. And their benchmarking suggests that, with further circuit improvements, this architecture could deliver up to 1,000 times higher throughput and nearly 100 times better energy efficiency than leading digital processors at the same precision. That does not mean this prototype can run every AI model 1,000 times faster than an Nvidia H100. It cannot replace a general-purpose GPU. The result applies to specialized matrix equation workloads, and the largest advantage is partly projected rather than fully measured in production hardware. Analog computing has always promised extraordinary speed. The missing piece was precision. Why digital computers dominated. A digital computer treats information as discrete values. At the lowest level, a transistor is interpreted as on or off. Software then performs arithmetic through carefully sequenced logic operations. Small electrical fluctuations usually do not change a 0 into a 1. Digital systems can use error correction, repeat operations, and store exact copies of data. Analog systems trade some of that certainty for direct physical computation. Imagine solving a mathematical equation by building an electrical circuit whose voltages naturally settle into the answer. The circuit does not need to execute millions of separate instructions. The physics performs the calculation as the signals move through the hardware. But real components are imperfect. Resistance changes with temperature. Amplifiers introduce noise. Manufacturing creates small differences from one device to another. The answer may be close, but not exact enough for scientific computing, communications, or modern AI. The Peking University team attacked the problem by separating speed from accuracy. One analog circuit produces a fast, approximate answer. A second analog operation measures the remaining error and corrects it. The system repeats this process until the solution reaches the required precision. What RAM actually does? The heart of the design is resistive random access memory. An RRAM cell stores information by changing the electrical resistance of a material between 2 electrodes. A low resistance state may represent one value. A higher resistance state may represent another. In this experiment, each cell supported 8 stable conductance levels, equivalent to 3 bits of information. The researchers used a 1 megabit RRAM chip for high-precision matrix vector multiplication and a smaller 8x8 RRAM array for low-precision matrix inversion. Both were fabricated using a commercial 40-nanometer CMOS platform. This was not a hand-built device assembled from exotic laboratory materials. The chips were produced through a foundry-compatible process, using 1 transistor, 1 resistor memory cells. An RRAM array can behave like a physical matrix. Each cell's conductance represents one matrix element. Input voltages represent a vector. When those voltages pass through the array, the resulting currents naturally combine according to Ohm's law and Kirchhoff's current law. The array performs matrix vector multiplication through its physical behavior. A digital processor would normally load data from memory, execute many multiplication and addition instructions, then write the result back. The RRAM array stores the values and performs the calculation in the same location. That reduces data movement and avoids much of the conventional von Neumann bottleneck. The matrix problem. Matrix equations appear almost everywhere in advanced computing. Wireless base stations solve them to separate overlapping signals from many antennas. Some neural network training methods also depend on matrix inversion or related linear system solving. A common form is A times X equals B. The matrix A and vector B are known. Digital methods solve this accurately, but the cost grows quickly as the matrix becomes larger. An analog circuit can produce a solution directly by placing the resistive array inside a closed feedback loop with operational amplifiers. However, the first answer is only approximate. The challenge is improving that result without handing the important calculation back to a digital processor. Earlier hybrid systems often used analog hardware for a rough estimate and digital floating point hardware for the precise correction. The Chinese team kept both major operations in the analog domain. How the two-stage solver works. The first stage performs low-precision analog inversion. Because the RRAM devices and supporting circuits are not perfectly accurate, the result contains an error. The second stage performs high-precision analog matrix vector multiplication. It calculates how far the approximate answer is from satisfying the original equation. That difference is called the residual. The solver then feeds the residual back into the low-precision inversion circuit to produce a correction. Each cycle moves the solution closer to the target. The researchers reported that precision improved by roughly 3 bits during each cycle, reflecting the 3-bit conductance levels in the RRAM cells. A 24-bit 4x4 real-valued matrix reached the maximum target precision after 9 cycles. Larger complex-valued problems generally reach the same precision within about 10 cycles. This is the central idea. The fast analog inversion does not need to be perfect. It only needs to be good enough that repeated analog correction converges toward a precise answer. The design accepts analog error, measures it, and then removes it. That is very different from pretending the hardware is naturally exact. How bit slicing builds precision. One RRAM cell stores only 3 bits, but the complete system reaches 24-bit precision. It does this through bit slicing. A high-precision matrix value is divided into several lower-precision pieces. Each piece represents a different group of bits and is mapped into a separate RRAM array. The arrays perform low-precision calculations in parallel or sequence. Their partial outputs are then shifted according to their significance and added together. It is similar to separating a large decimal number into thousands, hundreds, tens, and units. Each part is easier to represent. Combining the weighted parts reconstructs the original value. Bit slicing was already useful for analog matrix vector multiplication. The harder problem was applying high precision to matrix inversion, where the same simple distributive rules do not transfer cleanly. The researchers solved this by keeping inversion low precision, while using bit-sliced matrix vector multiplication to calculate the correction accurately. BlockAMC makes the design scalable. A physical RRAM array cannot grow without limit. Large arrays suffer from wire resistance, routing complexity, stronger currents, parasitic effects, and amplified noise. The team therefore used a block-based algorithm called BlockAMC. A larger matrix is divided into smaller submatrices. Different RRAM arrays store different blocks. The system performs a sequence of inversion and multiplication operations on those blocks, then combines the intermediate results. Using this approach, the researchers experimentally solved a 16x16 real-valued matrix inversion problem with 24-bit fixed-point precision. The relative error reached roughly 1 part in 10 million after 10 cycles. 16x16 may sound small compared with giant AI models, but matrix inversion is more difficult to map into analog hardware than ordinary multiplication. The point was to prove that a precise analog solver could scale beyond one tiny hardwired circuit. The block method also allows future systems to use multiple moderate-sized arrays instead of depending on one enormous analog network. The Massive-MIMO test. The researchers demonstrated the solver on wireless signal detection. Massive-MIMO uses many antennas at a base station to communicate with several devices at once. The received signals overlap. The base station must solve matrix equations to separate the different users and recover the transmitted information. The experiment modeled systems using higher-order 256 QAM modulation, which packs 8 bits into each transmitted symbol. That demands far more precision than earlier analog demonstrations limited to simpler modulation. The researchers transmitted a binarized image of the Peking University emblem through the modeled wireless channel. Their analog solver recovered the signal with bit error performance comparable to FP32 digital processing. For a 128x8 system, the detector reached comparable accuracy after only 3 iterative cycles. This matters because it connects the architecture to a real workload rather than only random laboratory matrices. Wireless communication, especially future 5G advanced and 6G systems, may require repeated matrix solving with strict limits on latency and energy. Where the 1000x claim comes from. The 1000 times figure needs careful explanation. The prototype did not directly defeat an Nvidia H100x1000 times in a complete application. The researchers benchmarked their analog architecture against state-of-the-art digital processors at comparable precision. Their model considered matrix size, array dimensions, converter overhead, amplifier speed, and block processing requirements. At moderate array sizes, the analog design already showed advantages for specific matrix-solving tasks. For larger optimized arrays and faster operational amplifiers, the projected throughput advantage could approach 3 orders of magnitude. Energy efficiency could improve by nearly 2 orders of magnitude. The paper also notes that BlockAMC reduces the advantage as matrices become larger because more stages and intermediate operations are required. Even then, the architecture remained ahead in the researchers' comparisons. The maximum result depends on better supporting circuits and dedicated integration. So the honest statement is that the demonstrated architecture could reach 1,000 times higher throughput for precise matrix equation solving. It is not evidence that an analog chip will make every CUDA workload 1,000 times faster. Why this could matter for AI? Modern AI depends heavily on matrix operations, but not every matrix operation is the same. Neural network inference is dominated by matrix multiplication. This chip focuses on matrix inversion and solving linear systems. Those operations appear in optimization, scientific machine learning, signal processing, and some second-order training methods. An analog solver could become a specialist accelerator. A conventional CPU or GPU would manage the overall program. When the workload reaches a suitable matrix equation, the system could send that task to the RRAM solver. The analog hardware would produce the answer quickly and efficiently, then return it to the digital processor. This is more realistic than expecting analog computing to replace digital machines completely. Digital hardware remains better for control flow, memory management, software compatibility, and exact general-purpose operations. Analog hardware may win by handling the narrow calculations where physics offers a shortcut. The honest catch: several engineering challenges remain. The low-precision inversion circuit still uses external components, including operational amplifiers, data converters, switches, and a microcontroller. The larger, high-precision RRAM array was integrated, but the complete solver was not one compact commercial chip. Scaling the inversion array beyond the demonstrated size requires dedicated design and fabrication. Larger arrays produce stronger currents and more complicated routing. Noise, wire resistance, device defects, and temperature variation must remain controlled. The system also needs programming and verification procedures to place every RRAM cell into the correct conductance state. Converters and amplifiers consume area and energy, and commercial software would need tools that identify suitable equations and map them efficiently onto the hardware. It does not prove that mass production will be easy. My take is that the breakthrough is not simply bringing analog computing back. It is making analog error part of the algorithm. The first circuit is allowed to be imperfect. The second measures that imperfection. Repeated correction turns a rough physical answer into one approaching digital precision. That is a powerful design philosophy. Future computers may not choose between analog and digital. They may combine both. Digital processors will coordinate the system and preserve programmability. Analog accelerators will solve selected equations using currents, resistance, and feedback, instead of long sequences of instructions. The 1,000 times estimate may shrink once complete commercial overhead is included, or better integration may allow the architecture to approach its projected advantage. Either way, this work moves analog matrix solving from a low-precision curiosity toward a credible specialist technology. So what do you think? Will analog accelerators become essential for AI, science, and 6G? Or will manufacturing variation and software complexity keep GPUs in control? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering breakthroughs reshaping computing. Because China has not built a universal Nvidia replacement, but it may have solved the precision problem that kept analog computing out of the modern chip era.